The last rule of counting that we're going to talk about is combinations. Now, combinations is actually very similar to permutations with one important difference. I'll illustrate it with this question. How many ways can 3 of 13 runners qualify for the finals? So we've got this scenario. We've got 13 runners. They're running the race, but this is a qualifying match. And essentially, we're going to take the first 3 finishers, first, second, third place, and they're going to go on to the finals. Now, do we care about what order they finish the finish line? No. All we care about is, are they one of the first 3 to pass the finish line? So in this case, 1, 2, 3 would have the same results as 3, 2, 1. Okay, so the order no longer matters in this case. So just as before, there are 13 ways that people can finish first place, 12 ways runners can finish second place, and 11 ways that runners can finish third place. So a total of 1,716 different ways that they can finish. But this was the calculation where we were dealing with first place, second place, and third place, where that order mattered. But for qualifiers, the order does not matter. So all of these different combinations that I have in this small table on the right side of your screen, they don't matter. They're all the same. It doesn't matter if it's 1, 2, 3 or 2, 1, 3 or 3, 1, 2 or any of those. All 3 of those will be going on to the finals because they finish in one of the first 3 spots. Order doesn't matter in this case. All right, so those 1,716 different ways that people can cross the finish line, each different way that they can be finished first, second, and third place, there are 6 different ways that those 3 people can finish the finish line. So what we're going to do is divide out all of those 6 different different rearrangements. There we go. We're going to divide out the 6 different rearrangements. So we're going to take the permutation of 13 runners selecting 3. So that's 13 times 12 times 11. And we're going to divide out the 6 different ways we can rearrange them. And that gives us 286. So bottom line, if we have 13 runners and all we care about are the first 3 winners, there are 286 different ways that those 13 runners can qualify for the finals. Okay, let's take it one step further. What about the top 4 runners? We're going to look at the way the 4 runners, top runners, and let them qualify for the finals. Well, then it would be 13 times 12 times 11 times 10. That's 17,160 different ways that the 13 runners can finish first, second, third, and fourth place. But there, the order still matters. Okay? If we say the order doesn't matter, then all of these different combinations can still happen. You can have 1, 2, 3, 4, or 2, 3, 1, 4, or 3, 4, 1, 2, or 4, 2, 1, 3. They're all the same. The order doesn't matter. And if you look carefully, there are 24 different ways that these can be ordered. So we're going to divide out all of those 24 different ways. So if we have 13 runners and we're going to do a permutation of the first 4, that'd be 13 times 12 times 11 times 10, which is 17,160. And then we're going to divide out the 24 different ways that they can be rearranged. That means there's 715 different ways that 13 runners can be organized into the first 4 places. Okay, so what did we do? Well, let me come here. This is the math that we use for both of those calculations. 13 permutation 3 and 13 permutation 4, but then we divided out the different number of rearrangements, 6 in the first case, 24 in the second case. But there's something interesting about these numbers. 6 is actually 3 factorial. And 24 is actually, hopefully you guessed it, 4 factorial. That's the number of places that we're trying to select. So we can actually take the permutation and divide it by the number of places we're selecting factorial, and that gives us a combination where the order doesn't matter. Here's the full equation. Now I'll point this out here. This part right here, we've seen that. That is our permutation. That's just n permutation r. All we're doing now is we're dividing out r factorial. In other words, we're dividing out all the different ways that my selections can be rearranged among themselves. Okay, that's how you do a combination. Okay, let's look at this in another example. Let's win the lottery. Well, I'm going to show you. You can actually see on the screen. That's a bad idea. Let's not do the lottery. But here we go. A certain lottery has numbers 1 through 49. You get to select 6 different numbers on your bubble sheet. The computer reads them, and if your 6 numbers match the lottery's 6 numbers, then you win. But the order does not matter. It doesn't matter if you picked 1, 10, 20, or if you did 10, 1, 20, or 21. The order doesn't matter. All that matters is that your 6 selected numbers match the 6 numbers of the lottery. So now that you have your ticket and you've filled out the numbers, what are the chances that you're going to win? Okay, chances means probability. Remember how we do probability? Probability is the number of successful outcomes divided by the total number of possible outcomes. All right. So how many ways can I fill out a lottery sheet? Well, here we've got a combination. Total number of outcomes is going to be 14, choose 6. That's a common way to say this. 49. Did I say 14? I'm sorry. I meant 49. 49 combination 6, or a very common way to say it is 49 choose 6. Because of our 49 numbers, we are randomly choosing 6 of them. Okay. 49 choose 6 is going to be 13,983,816 different possible combinations I could select on a lottery ticket. How many ways can I win? Well, the lottery machine has to have the same 6 numbers as I have. There's only one way that you can win the lottery. Okay? So what's the probability of winning? How many successful outcomes are there? 1. How many total number of outcomes are there? 13,983,816. And when you do that, you get 0.000000715, which even if you put that into a percentage, that's 0.0000715%. Okay, that's awful. Okay. Gambling in general is not a good idea. I mean, we could talk about a lot of gambling here in statistics and show you it's a bad idea to gamble. And maybe we'll do that with when we get to probability distributions in lesson 12. But of all the ways to gamble, the lottery is the dumbest way, okay? Because your probability of winning is extremely small. Okay, there's your moral speech for the day. Point of this was using combinations as a solution for winning the lottery. And so now you have seen how to use combinations in a real life situation.